Hi everyone and warmly welcome to this RanLOS webinar. Today we're going to present our view on how to do OTA measurement within the automotive industry. So the agenda for today is to give you a short introduction of our company, then we'll go through the measurement system and our software, and then we also have passive and active measurement data as well as videos, and then we have a few minutes for conclusion and wrap up and also for questions. My name is Louise Rosdahl and I'm the CEO of RanLOS. Today I also have Professor Jan Carlson with me. He has more than 30 years of experience from EMC and antenna field. He is a member of the International Steering Committee of EMC Europe, and he is also an adjunct professor at Chalmers University of Technology. I also have our sales director, Mr. Lars Granbom. Lars, he started off at Ericsson many years ago. Then he has been a successful entrepreneur in multiple companies within antenna design and measurements. So some of you might have heard of our founder, Professor Per Simon Skildal. He was active at the Chalmers University of Technology. He was a visionary but also a very successful businessman, introducing ComHat technology and also building the companies Blue Test and Gapwaves. And he is also then the father of RanLOS. And he came up with this idea of an accessible and easy to use OTA equipment using random line of sight technology in 2013. Then he applied for multiple patents around the globe, which we now have today in the company. And then the products have been developed during the past years, for instance, in a Swedish government-funded program together with Volvo Cars and some other partners. So that is a little bit about our history, and now I will hand over to Lars, who will present our products more in detail.
Thank you, Louise. My name is Lars Granbom, and I am responsible for sales and marketing at RanLOS, and I want to present the products. At the left, you see the RanLOS Sub-6 system, which is a large test system designed to be measuring large objects such as vehicles, cars, motorcycles, etc. The test system covers all relevant standards such as 3G, 4G, 5G, etc. and frequency bands from 700 MHz up to 6 GHz. It's an upgradable system, means that we can cover higher frequencies in the future if that is needed, or other standards which is not available today on the market. The system is designed to be used in existing chambers such as EMC chambers or similar, or at more simple test environment places such as the development department at the customer site, for example. The next system is what we call the millimeter wave system. In this case, a 28 GHz system designed to be used to test smaller objects. For example, handheld devices, small base stations, etc. This is also a upgradable system. This means that we can cover higher and lower frequencies when that is needed. The last product I want to present is the software, and the software is used to control all the measurement setups, the instrumentation used, and the turntables or the positioner that you are using together with the measurement. This is how it works. A dual polarized linear antenna array is feeding the cylindrical reflector, which is converting the wave to a planar wave, simulating a far field environment for the object that we are testing. Comparing with the real world, the RanLOS system simulates a line of sight environment. Communicating with a distant base station, the dominating wave is arriving at the car in a randomized angle. If you compare with a mobile phone, communicating inside a building, you have a totally different environment that we call rich isotropic multipath environment. This open environment that we see on the picture is the one that we think is the most used in this kind of use cases as we see here. The system consists of an antenna array and a cylindrical reflector, as we said before. The antenna arrays are easily changeable. We have today antenna arrays from 700 MHz up to 6 GHz. If we in the future want to have higher frequencies, it's easy to change the antenna array to an array with high frequency antennas. The object that you are testing is placed on a turntable, and the turntable can be equipped with or without dynamometers. So this is a simulation of the real-world usage of the car in this case. And by this I hand over to Jan Karlsson.
Thank you very much, Lars. So my name is Jan Karlsson and I'm the CTO of RanLOS. And I would like to focus a little bit more on what we actually can use our test system for. So we will start with what we call passive measurements. And that is that we can measure antenna radiation patterns. As Lars mentioned before, our system creates a plane wave, thus simulating far field conditions, which means that we easily can measure antenna radiation patterns, such as antenna gain, for instance. And you can see the setup on the picture to the left. So for this measurement, we use a vector network analyzer. So one port of the vector network analyzer is connected to our test system, and the other port is connected to an antenna on the equipment under test. And then we have a computer controlling the test instrument, and the computer will also control the turntable in this case. So here is shown one comparison that we have done. We have of course done a lot of comparisons, and to the picture to the left you can see the measurement setup with our test system, our sub-6 test equipment, and on the turntable it is placed a body of a car. And then we have several antennas on the roof of the car. In this case it was simple monopole antennas. So we did the measurement in this test site, and the test site is at Volvo Cars in Sweden. So we did this in a research project together with, among others, Volvo Cars. On the picture to the right, you see a very advanced measurement site in Denmark. So this is a near field to far field measurement range. So in this case, you scan the whole half sphere around the car with a near field probe. And from the result, you can later on calculate the far field radiation pattern. And as you can see in the picture in the center, the agreement between these two measurements is very good. And it should be pointed out that our equipment is very fast, and it's also less expensive than the advanced measurement facility that you can see to the right. So this is just one example. So we have a lot of examples showing that we actually can measure antenna radiation patterns. And of course we can perform different types of measurements. If you have a multi-port, for instance a 4-port network analyzer, you can, if you look to the left, you have a single polarization measurements. That is, you connect one port to our test equipment, and then you can measure 1, 2, or even 3 antennas simultaneously. So you can measure 3 antennas on the vehicle during one measurement. And to the right, we have setups for dual polarization. And in this case, you connect 2 ports of the vector network analyzer to our test system. And then you can measure the 2 polarizations simultaneously for a single antenna or for 2 antennas on the vehicle. So we have different options here. So that was the passive measurements, and now I would like to mention a few words about active measurements. And by active measurements, we mean that we measure communication performance. That could be block error rate, could be throughput, or other parameters that you're interested in. And this could be 3G, 4G, or even 5G systems. It only depends on what kind of communication test instrument you have. So on the figure to the left, you see one possible setup, and this setup is for a 2x2 MIMO measurement. So we connect 2 ports from the communication tester to the RanLOS test equipment, and then the base station will communicate with the car, and in the car you have a modem that is communicating back to the system. So by this setup you can measure, for instance, throughput, and you can see an example of throughput curves on the picture in the lower right of this slide. So you can see you have several throughput curves, the narrow lines here, and that is the throughput for different angle of rotation of the vehicle. And then you have also a thick line, and that is the mean value of all these curves. So on the y-axis you have the throughput in percentage, 100% at the top and 0 at the bottom. And on the x-axis you have the power level. To the right you have a high power level in the downlink, and then the power decreases towards the left in the figure. So what you can see is that for a high power you have 100% throughput, and then suddenly at some power level the connection is lost. The throughput goes down to 0. So that's active measurements. And of course, also for this, we have done comparisons with other type of measurements and also with numerical simulations. So here you can see one example, and you can see the vehicle and the test setup to the left in the figure. And this was also done in the research project together with Volvo Cars. In the center figure, you can see actually 4 curves. You have the blue curves representing measurements, and one is solid and one is dotted. And these 2 curves represent different modems on the car. So it's a different antenna system, you can say, on the vehicle. And the turquoise lines represent numerical simulations, and that is quite complicated simulations that we have done in a numerical tool. And that is the picture to the right. But once again, you can also see that the agreement is very good here. So measurements agree with simulations. So we are confident that our equipment works very well for both passive measurements and also for active measurements. And also for active measurements, we have different setups that are possible. Starting from the top left, you have single receive antenna on the vehicle and also single antenna on the base station side. So this is the SISO, the 1x1 setup. Going down, the picture in the lower left on this slide, there we have a single receive antenna on the vehicle and 2 antennas on the base station side. So in this case, 2 ports of the communication tester are connected to our test system. Top right picture shows a CMO, that is 1x2 measurement setup. So you have 2 antennas on the base station side and 1 antenna on the vehicle. And finally, in the lower right corner, you see the setup for the MIMO, that is a 2x2 MIMO measurement. I can also mention that the extra antenna you can see on all the active pictures that were shown, that is used for the uplink, so that we can guarantee a stable connection all the time Okay, so now you have seen that we can perform two different types of measurements. That is passive measurements for antenna radiation pattern and active for communication quality measurements. And everything is controlled by our software, and the software is easy to use, and you simply follow 5 steps. In the first step, you select the setup, and that is, you select from a number of passive or active setups. And in the second step, you select the measurement instrument that you will use. And that could be either a vector network analyzer or a communication tester. In the third step, you select the positioner, and in the case of a vehicle, that is probably a turntable. In the fourth step, you perform the measurements, and in this step, the software controls the instrument and the positioner and collects the data, which is saved in files. And in the last step, you can analyze the results in many different ways. You can plot the results in different formats. So in the first step, you select the setup, and here we have a number of setups predefined in the software for what we call passive measurements, that is for radiation pattern measurements, and we also have different setups for active measurements, for instance, throughput measurements. So we have a number of predefined setups in the software, but you can also easily create your own setup in the software. So that can easily be done. So that was step 1, and in step 2, you select the instrument that you will use for the measurements. And for passive measurements, you select one of the vector network analyzers that we have implemented. And if you cannot find your vector network analyzer in this list, we can develop a driver for you. So the software is modular, so it can be extended to new instruments. You can also select between different types of communication test instruments. And today we support testers from Rohde & Schwarz and also Anritsu. And in the future, we will also support 5G test instruments. So in the third step, you select your positioner, and perhaps you only have one positioner, and that in that case, that might be the turntable in your chamber, for instance, in your EMC chamber. So then you select a driver for that, and if it's not included in the list here, we can develop it for you. And the communication between the software and the turntable can be either a serial communication, it can be GPIB, or it can be TCP. So we have different options here. So in the fourth step, you just start the measurement, and in this case, the software will control the instrument, and it will also control the turntable. So the vehicle will rotate, and it can rotate either continuously or rotate in steps. And when the measurement is done, the last step is to analyze the results. And here you can plot the results in many different ways. You can plot it as simple 1D curves, like the polar plots shown in this figure here. Or you can plot it as a full 3D radiation pattern, or also as different kind of surface plots. So now we would like to show a video. So this video will show the passive measurement, and that is measuring radiation pattern from a vehicle in this case. So the first step is, of course, to set up the measurement equipment. And here you can see the measurement site at Volvo Cars. And in principle, this is an weather-protected outdoor measurement range. You can also see here that the sub-6 system is placed on wheels, so it's quite easy to position it in front of the turntable at the test site. So if you have an EMC chamber, you can easily roll it out or in the chamber. The next step is to mount the linear antenna array feed. Here you can see all the antennas, in this case 32 antennas, dual polarized antenna elements. So when everything is set up, you are ready for the calibration. So you connect the vector network analyzer to the RanLOS test system, and in this case we have a 2-port vector network analyzer, so we connect to only one of the ports on the RanLOS system. In the next step, you measure the height of the antenna that you would like to measure. In this case, we would like to measure an antenna placed on the roof of the car. So we measure the height, and then you take a reference antenna, and that is an antenna with a gain that you know, and we place it on the same height as the antenna you would like to measure. And we place the reference antenna at the center of the turntable. And in this case you can see that it's a biconical dipole antenna. So now everything is connected and you are ready for calibration, that you will simply do by using a special procedure in the software. So the software will control the calibration. So first you calibrate for one polarization, and then you rotate the antenna 90 degrees to calibrate the other polarization. And since we only have a 2-port vector network analyzer, we need to reconnect the cable. Now it's time to perform the actual measurement, and in the first step you position the vehicle under test. So you position it on the turntable, and then you should connect the antenna, and here you can see the coaxial cable coming up from a rotary joint in the center of the turntable. So you connect the vector network analyzer to the antenna in the vehicle. So now everything is set up for the measurement. So you select the setup, you select the instrument, select the turntable, and then you simply press run in the software, and the measurement starts. And as you can see, the vehicle is rotating on the turntable, and it could be a continuous rotation, or it can be rotated in steps. And here is the vector network analyzer taking the frequency sweeps. And when everything is done, you can analyze the results. Here is shown a surface plot where you have frequency on one axis and the angle on the other axis. So it's very easy and fast to do a measurement. So now we would like to show another video, and in this case it's a video how to perform active measurements. So the first steps are the same as for passive measurements. So you do a calibration and so on. And then you position the vehicle under test on the turntable, and in this case you do not need to connect any cables to the vehicle. The vehicle will communicate with our test system. And this is the setup that we showed before. This is the setup for 2x2 MIMO. So we connect the different antennas to the communication tester. First we connect the downlink antenna for stream 1 to one of the ports. Then the downlink antenna for stream 2. These are the two cables going to the RanLOS test equipment, and then we have the uplink antenna. And then you select the measurement setup, and in this case an MIMO 2x2 setup, and you can here set different parameters such as which system you would like to measure, in this case LTE, which parameters to measure, and also how the turntable should be rotated. And in this step we select an instrument configuration file. That is a file that will perform a lot of different settings on the instrument. So here you can see the different settings, and you can also see that the configuration was successfully completed. So now you are ready for the measurements. So you simply press start in the software, and here you can see a table. In the leftmost column you have the power, so you start at a high power and then the power is decreased until you lose the connection. And then you can see that the vehicle is rotated in steps. So here you can select, of course, the size of the step. I think in this case we used the 5-degree step, but you can use whatever you like, of course. So here you can see that the relative throughput goes down to 0, and now the measurement is completed. And now you are ready to plot the result. So you select the result file in the left part of the software, and then you select which parameter you would like to plot. And in this case I select the relative throughput as a function of power level, and then you select one of the different rotation angles. So here you can see the relative throughput for one angle, and then you can select some other angle and add it to the same plot. So now we have two different throughput curves for different rotation angles. You can also go to a data analysis possibility in the software, and here you can once again select what you would like to plot, the relative throughput in this case, and I would like to plot it as a function of power. So I would like to have power on the x-axis, and then I can also select which curves I would like to plot, and you can see that we have 37 different curves in this case. So I would like to plot them all, and here you can select different analysis, but to start with I just plot all curves, and that we can do by simple click on a button. Here you can now see 37 curves for the different rotation angles of the vehicle, and you can see that they vary, of course, depending on the rotation angle of the vehicle. And this is just one example to show that we can do some analysis, and you see the thick curve here is the mean value of all curves. And you can also do other types of analysis here, standard deviation and so on. So that's the active measurements. So now I would like to hand over to Louise again.
Thank you so much, Jan, for guiding us through the videos. So this is what we currently support. Then in our future plans, we will also develop our equipment towards 5G, for instance. So we have already done testing with 28 gigahertz feed array. And as you can see in the graphs here, the antenna manufacturer data is very similar to the measurements that we have performed. And it's also very easy for us to integrate 5G instruments into our software, since it's done by the same approach as the current instruments that we support. So in summary, the test system that we have is accurate. It doesn't require an advanced test chamber. It's accessible. It can be used on an everyday basis. It's easy to use for test engineers, and you don't have to have a specialist education. The software is 5 simple steps, for instance. So what we would like to offer is the possibility to test earlier, test more frequently, and as often as needed, to enable testing during the whole development process. So thank you very much for listening in today, and now we will open up for questions. Thank you.